Wasabi, you guys. I'm going to show you 10 no-nos, or 10 things to avoid when practicing integration B. First thing is using textbook integral problems. Alright, now let's be honest. You're let's say you work on a chapter which is about strategies of integration techniques or whatever. And then you decided, okay, you know what, let's find some more advanced integrals, and you go to a computer algebra system chapter. You start doing these tedious problems, or maybe other sections from like integration by parts, partial fractions, trig integrals, and then you work on more tedious problems like solve compute sine 8 of 3x dx. It's just like it's like this. These are just like tedious problems. Look, this you'll never come across these tedious problems in integration B. Like you're not gonna come across a problem like this, and then it's like what, x cubed plus 1. Then you have x plus 2. All right, integrate this. Like, no, you're not gonna you're not gonna come across these nasty integrals. Like, don't fully rely on calculus textbooks. Some calculus textbooks, they do have some good problems, like things like compute the integral x ln of x. They're like, that's okay. But tedious problems like these, like, skip. Like you're never going to come across these problems in integration B. Most problems in integration B is about a sneaky trick, right? Every problem in integration B, there's a purpose to why it's there. There's a purpose to, and there's going to be a very sneaky trick that involves into it. Sometimes there are sometimes there are like other competitions where they do use tedious integrals like this. Then I'm sorry. I'm sorry. I'm very sorry. And that's you're just gonna have to pray. And whoever chose this integral and put it in the competition, you are a menace. So but don't use textbook integral problems most of the time, because they're just they're good for like making your background knowledge very solid, like basic techniques, right? Like that's like, it's good for like that, like practicing like the basics and like becoming super comfortable with it. But problems like this, like it should not come. This should not be an integration B. Like this is horrendous. Second thing is graphing, or literally just sketching a graph. Okay, something like this. Okay, this I understand, right? Because then it's just to help you sort of understand what the heck is going on, right? You'll do a graph, okay, graphing, because it's absolute, it's going to look like this. So we're technically taking 0 to what, or some interval, and then you're just going to multiply that multiple times to whichever 2 pi, whatever, right? So that graphing, it's like a last resort thing, but you should not overly do it. Like I remember there was an integral, I forgot what bounds it was, but it was like more absolute value stuff like this. And then some high school student was literally graphing this function. Literally was graphing this function and computing this integral geometrically by using like squares or rectangle. And I'm just like, like it's gonna take a long time. Like, come on. Like, you're really, like, this is not a simple graph. This is not a simple function. So when they graph it, they were plotting points. They were plotting points depending on the bounds. Okay, from A to B, starting with whatever number, and they started plotting points and graphing it. And it's stop. Okay, you're gonna be eliminated. Your opponent is going to literally get to the answer before you can. So don't. I like to do everything algebraically, equationally. I don't like graphing, especially if you're given a nasty graph like I don't know, like e to the 1 minus x squared minus ln of sine, like whatever, blah blah blah, and you're trying to like approximate the area or solve this geometrically. Like, please, like, I highly doubt you can graph this. Like, let's not try to be a human graphing calculator and like, oh, maybe it's like this. Like, no, just don't. Okay, you're gonna be inaccurate. It's not good. So I would not rely on graphing, sketching. Learn to do things algebraically. The third thing is approximating. I'm not even gonna explain. Like, come on. In integration B, you're gonna have to give an exact value. You cannot approximate. You can't just do that. Like, no, you can't just only memorize the Riemann sum, or using freaking trapezoidal rule and like, oh, it's like 1 point whatever. Like, you can't do that. No. and that's also gonna take a long time. That's gonna be like what, a tedious process, because you would have to do like delta x times and then plus. It's just no. Just don't even try. Okay, there are competitions like Harvard, MIT, where they do things like, okay, I need you to approximate, I need you to estimate this, but like, okay, first of all, Harvard, MIT, this is just a bit unfair, and this is not. I don't find this fun. Okay, approximating, really? Come on. Like, really? Come on. Let's not do some estimation problems. And just, yeah, in general, don't practice approximating. Don't use it at all. Just don't. Number 4 is, oh my god, number 4 kills me every time. Number 4 is literally learning 5-second G-main tricks. Okay, here's an example. You watch, like, you search up, like, come on, just admit it. You search up like integration shortcuts to practice for integration B. You search up integration shortcuts and you come across these Indian videos, and they're like, all right, we're gonna have to solve this integral in like 3 seconds just by memorizing this formula here. Like, you can, okay, look at this. You're really gonna memorize this whole formula just for this very specific integral case, a very specific integral case where it's like, you have to be so lucky to hope that this will come in the competition, and then it's just so that you can perform this in 3 seconds. And it's okay, it's not gonna look, I get that you want to solve this in 3 seconds and show off to the audience, like, but it's not worth it. Okay, this is not worth it. Okay, it is not worth it. Do not use G-main videos to learn 5-second formulas. Stop it. No, don't do this. Okay, no, bad, no. Okay, here. You can literally solve this in 10 seconds, or maybe anywhere less than 30 seconds, honestly. In the best integration B practice, instead of memorizing the answer, memorize the process, the step of it. You know, for example, like, and if you keep doing that, you'll soon, when you keep doing it so many times, you just end up memorizing the answer. Like for example, this integral here, okay, the integral of inverse sine of x, this is equal to, that's like, what? Plus 1 minus x squared. You see how to you, it looked like I memorized the answer. Like I'm trying to take it out of my memory and, you know, oh, okay, that's the answer. Like it looks like I just memorized this by heart. But no, I did not. I was actually integrating by parts in my head because I memorized the process of integrating it. So that's what it is. And because this comes out a lot in integration B, like I'm so comfortable memorizing this process that it's just okay. I know how this turns out, and then you can just do it mentally. So memorize the process. Okay, don't try to do things mentally unless you're very comfortable. But memorize the process. Okay, I see this integral. I know exactly what to do, and you do it fast, right? Okay, this is x. This is y minus x squared. This is a negative. Okay, here, this integral here, this is a u substitution, I know that. Du u 2 because of the x squared. The minus because of the negative, so the negative cancels out. Okay, and then this is, wait, no, oh yeah, square root of u plus c, and then you get this. So, like, that's what a beginner would look like. And here, let me go ahead and demonstrate solving this without memorizing the formula, and look how fast this would be. Okay, this is, I'm gonna go like this. And this is like, I know what the bottom looks like. I need cx. I want to do plus t, dA minus dA. So I already know where this comes out to. So I'm purposely making this a. This is all constant, blah, blah, blah. Okay, so this is ACX plus C, CX, please decide to do U substitution. Make sure to bring out the constant because of that CX. Okay. So you see how I didn't memorize the formula? You could still solve this very quickly, right? And again, because I come across these type of cases a lot in integration B, like I memorized the process, you know exactly what to do. So again, memorize the process, and you can still be fast. Okay, it's not 3 seconds. It didn't take me 3 seconds, but it definitely took me less than 30 seconds. So, you know, don't rely on memorization sometimes, especially formulas like this. Like, just no, please, for God's sake, do not memorize this entirely. Memorize the process of the integral. Okay. Number 5 is overly complexifying the integral. Okay. Now, in some cases, like there are some types of integrals where it is better to complexify, right? Like that's not good. This one. Like, how many times have you seen this? A lot in integration Bs. Okay. This, then yes, you would complexify. So certain cases, certain specific cases, it's best to complexify, and you just, again, you memorize the process of those types of integrals. Okay, but I've seen others where, okay, let's go ahead and do e to the x sine of, let's say, 7x, or make this a 4x, right? Okay, this is ugly, right? And people would be like, okay, well, let's complexify this, and we go ahead and, you know, we get like x of 4 plus 7i, something like that. But the thing is, the reason why I don't like this It's because then you're gonna you're gonna have to deal with like conjugating. Or like some nasty whatever, I don't know. And then you have to like conjugate all this. You have to conjugate all this and then turn it back to a real number or an imaginary part or whatever. It takes forever, and you can definitely easily lose track of constants, and like just for having a wrong answer, you'll be eliminated very easily. So this is very inaccurate. I I personally don't like complexifying integrals only for certain specific cases. But things like this, right? I will never complexify the integral with using this method because this is scary. Okay, if I was to come across an integral like that, I would just do integration by parts. Just because it's just easier. Okay, sine of 7x. This is 7c. 49s e to the 4x. I know it's going to be e to 4x all the time. 1/4, 1/16. Okay, so I know that my I, this integral, the original integral is I equal, we have here, so it's e to the 4x, okay, of sine of 7x over 4 minus 7 cosine of 7x over 16. Okay, and then I have minus 49 over 16i, and then take the I. This is what? What's 16 plus 49? I don't know. That's like 65. I don't know. 65. So I would divide 65 to, whatever, right? So again, ugly, nasty constants, but I would prefer doing it this way because it's just a lot faster. And you just, okay, well, because it's 65, I'll just go ahead, divide everything by 65. Okay, erase this. Write down my constant. And then you're done. So I don't always rely on I get it, complexifying the integral, it's satisfying, but it is a nasty load of work. Unless you're very good at complex algebra, then go for it. But people like me, okay, don't overly complexify integrals. Okay, don't overdo it. Do not overdo it. It's not always the fastest route. Right. Number six is literally doing long polynomial division. Okay. Oh my goodness. There was one time where I saw someone who had to integrate this, and they used polynomial division with e to the x, and I'm just like I was just like, ugh. like that's nasty. Like let's not do that, right? All you really have to do, well, what we have here is we have 1 e to the x, I'm just going to put a dx here, right? So we have 1 over e to the x plus 1, just add e to the x minus e to the x, and all you get is, let's see, this cancels out, right? So this is 1 minus e to the x. This is just a u substitution, and you're done. In fact, you can do this mentally too. So don't in some cases it's good to use polynomial division, but long polynomial division is like a last resort thing, and it's a huge no-no. But it's best to get used to doing zero substitution. Things like x squared plus, this is a common thing here, right? Students would see this and be like, oh, okay, well, we were taught in class that we just use polynomial division. Okay, but come on, there's a faster way. We can, I forgot the term, but pretty much make the numerator similar to the denominator. So, okay, x squared plus 1, can we put this in terms of x squared plus 1, or maybe in terms of its derivative? Yes, I can, right? Yes, I can. x plus 1, okay, and then plus 1 because of that 2, and then plus x, okay, this cancels out, this is an inverse tangent, and this, I could just do a u substitution. So here, I just get x plus inverse tangent plus a half of ln of x squared plus 1 plus c. I don't know why I wrote it curvy. And then you're done. Oh. Yeah. So, polynomial division, it's meh, last resort. The only time, I don't really consider this polynomial division, but it technically is polynomial division. There's things like, you'll come across things like this, and then you would have to, okay, polynomial division. But geometric polynomial division is something that's an entirely different story. I have that as a separate category. Polynomial division in general, please don't use it in integration B. It's like a last resort thing. Sometimes, I mean, if you're in an integration B competition where they do give you like textbook problems and you actually have to do it algebraically, then I'm sorry. But mainly integration B problems, they're supposed to be for like sneaky tricks and fast stuff. Like there's a purpose, rather than, oh, we're just gonna throw this at you and see how fast you can do it. It's, it shouldn't be, integration B problems shouldn't be about bashing. Some cases, yeah, like tiebreakers, but like it shouldn't be like nasty tediousness. Number 7 is using the triangle in trig substitution. In some cases, if you're given problems like this, right? If you're given problems like this, then yes, go ahead, use the triangle. Because, I mean, you're gonna have to simplify this, right? Or you can let u equal inverse tangent of x, right? And then you get cosine of u. And then you get what? Tangent u is equal to x, so dx secant square u. Okay. Okay, so then you get du. So then this is equal to secant of u du. Okay, and then you can integrate from there, right? So that's more of an advance. That's more of a force u substitution. But when you're doing a regular problem like this, right? And say like, okay, you use trig substitution. It's not actually equal, but like I'm just gonna give like a random answer, like sine of 2 inverse sine of x, and then plus ln of secant of inverse tangent of x over 2 plus tangent of whatever, right? Things like this. Just leave your answer. Just leave your answer like this. Don't waste your time. Oh, I'm gonna make this, okay, let's see, triangle. No, just leave your answer like this, okay? Unless it's like Scranton University, where you have to simplify everything, then I'm so sorry for you. But honestly, in most integration Bs, you should not be forced to simplify. Shit, some people even put their answers in zeta form rather than pi square or whatever, So you should not be forced to simplify things. So take advantage of that. Go ahead and just leave your answer as this, or leave your answer as like this. Like just leave it. Okay? It's not worth just using the triangle sub and simplifying it, and then it's like, oh wait, but you have the answer right here, you just want to simplify it, but then someone beats you to it and it's like, oh well, you're eliminated even though you have the answer first, but you decided to simplify it further for no reason. So Don't use the triangle. Just leave it like this. All right. Next, number 8. This is just ridiculous. I'm not even going to talk about this very long because it's very obvious. And that's using Darboux integration. If you haven't taken real analysis, then just skip this. Okay. But this is just to all those trolls out there. Come on, really? Darboux integration with whatever this is, or etc. Come on, like, like just stop. Okay, don't even try. Don't even teach people using Darboux integration and trolling them. No, stop. Okay, don't. If anyone tells you use Darboux integration for complicated integrals, don't. It's not even computing. It's just it's just the backbone of an integral. Just don't. Okay, don't do Darboux integration. Number 9 is using Euler substitution. Oh my goodness. Oh my goodness. Euler substitution. There was an MIT integral. It was like x plus square root square plus, I think this is it. It was like 2. Okay. Someone used Euler substitution, and I'm just like, ew. Okay. I get it, you want to practice for integration B, something competitive, but do not learn Euler sub. I mean, if you want to, if you're that committed, but it's nasty. It's memorization. I'd rather have you memorize, study learning to use Weierstrass. The Weierstrass substitution, where like u equal tangent. Memorize this. Memorize the formulas for this. Okay, but don't memorize the formula for Euler sub. It's not. Just no. Okay, it's one of these. Euler substitution is one of those textbook type of problems. You know, it's tedious. Again, you're not going to come across an integral using Euler sub at integration B, and if you do, then who the hell hired that problem writer? But again, like, no, do not use Euler substitution. It's not worth it. Okay, it's not worth it. It is stressful to learn it. It is just memorization. It's complicated. It's nasty. It's satisfying to use it, but just don't. Okay, it's not worth it. Okay, you're hardly ever gonna come across an Euler substitution integral. Okay, and in fact, this is not. I mean, you can use Euler substitution, but for easy sakes, this is a hyperbolic substitution. So this is also one of the things where beginners should get used to, is doing hyperbolic substitution. Yeah, you're never going to come across Euler substitution integrals like things like this. Like, you'll never come across that in integration B. Okay? No, you're not. Okay? And if you do, that problem writer should be fired. Because this is not okay. This is just tediousness. You should not be forced to learn Euler substitution. Okay? That's ridiculous. Right? Not even what's that? What's it called? Ostrich method? It's a long ass word. It's like Ostrovagaski. Whatever this, it looks like this. The word looks like that. And it's a partial fractions method. And again, like, things like, don't learn it. It's tedious. These are all textbook methods. Just don't. Okay? You'll never come across these in integration B. And the last one, number 10. This one annoys the hell out of me. Let me actually get something, actually, because oh my god. Number 10 is literally memorizing integral tables from calculus textbooks. The amount of high school students I saw bringing their calculus textbook, memorizing their integral tables, and I'm not talking about standard integrals. I'm talking about things like this. Okay, like, oh my god. I have my book with me, and this is just absurd. And they'll they'll come up to their friend and they're like, oh bro, I'm like memorizing all these integral tables, and I just memorized this formula here. It's like, and then they literally memorize all this nonsense. Oh my god, this is so disgusting. B minus C, B plus C, tangent, pi over 4 minus ax2. Oh my god, I'm not. Oh no, I am done. Plus C. Okay, let's be real. Okay, like since when will you ever have to use this? Oh my god, the amount of high school students memorizing integral tables, bringing their calculus book to an integration bee and memorizing these tables, and yet they still lose because they can't solve this. But oh my god, Jesus, please, for the love of goodness sakes, do not use integral tables. Do not memorize integral tables. It is not worth it. Okay, just no. Stop. Okay. Oh my god. Or what's a good integral? Another example. Like, oh my goodness. There's this dude. He was like, yo, I just memorized what is it? It was like freaking x square root of 2ax minus x squared dx. And the freaking answer is like long. Oh god, x plus a 2x minus 3a. Oh, that's it. That's a square root. Oh dear god. 2ax x squared all over 6. I'm not even done. Look at this. A cube over 2 inverse sine of x minus a over a, and then plus c. Come on. Please do not be like these high school students. Okay? Do not memorize integral formulas. Do not do this at all. Okay? Don't try to show off learning, you know, oh, I could do this in like 3 seconds. No, you're gonna be writing all this in like 25 seconds. Okay, just no. Don't practice like this. Don't practice like all of these for integration bees. All right. Thank you guys so much for watching, and I'll see you guys in the next video.